Hi. One of the most classic problems in mathematics is solving equations, f of x equals 0. But what does it mean to solve an equation? In this video, we'll explore one of the most beautiful and profound results that provides a method to tackle seemingly impossible equations. In popular understanding, solving means finding the exact value of the solutions. So, for example, the equation 3x plus 2 equals 0 has solution x equals minus 2/3. The second degree equation x squared minus 5x plus 6 equals 0 has solutions x equals 2 and 3. In cases like these, we have a general formula. For instance, for quadratic equations, ax squared plus bx plus c equals 0, with a different from 0 to have a proper second degree equation, we have the well-known formula. Also, for cubic equations and for quartic equations, we have a formula that depends on the coefficient of the equations through algebraic operations, including extracting roots. However, in the early 19th century, Ruffini and Abel demonstrated that starting from equations of degree 5, it is generally impossible to find such formulas. This situation commonly arises with non-polynomial equations. For example, take this simple equation e2x plus x equals 0, that we can also recast as e2x equals minus x. Under this form, we see that x represents the abscissa of the intersection between the exponential function and the bisector of the second and fourth quadrants, and this equation cannot be solved explicitly. However, looking at the graphs, it seems evident that solution exists. The line descends from plus infinity to minus infinity, while the exponential rises from 0 to plus infinity. It appears clear that the two curves must intersect at some point x star negative. And in fact, if we define f of x, this function, we can see that this function is positive for x positive and negative for x less than minus 1. So it seems natural that a solution must exist between minus 1 and 0. But how to prove it? In 1817, Bolzano demonstrated a general theorem guaranteeing the existence of solutions to such problems. So let f be a continuous function on the interval ab, such that f takes values with opposite sign at the two endpoints of the interval. So one value is positive, the other is negative. Then, as the intuition suggests, somewhere in the middle, the function will take the value 0. So this means there exists a solution to the equation f of x equals 0. Moreover, Bolzano's theorem identifies a method for determining the solution. This method, which is called the bisection method, can be easily implemented on a computer to provide approximate solutions with controlled error margins. Let's see how the algorithm works. We assume that, for example, f of a is negative and f of b is positive. The first thing we do is to compute the midpoint between a and b. And then we evaluate the function at that point. We may be lucky, the value of the function is 0. This means that we found the solution and the search is over, so we just stop. Or the value of f at point x1 is different from 0. If it is positive, as in the figure, we could restrict our search in 1/2 of the initial interval, so let's say on the subinterval from a to x1. So we define a new interval, a1, b1, as a to x1, and then we repeat the step on this new interval. If the value of the function is negative, we do the same, but with the interval from x1 to b. So we define a new interval, x1 to b, and then we repeat the step. So this means that the next step will be to recompute the midpoint now of the new interval that we is just half of the initial one. We evaluate f at that point. We check if it is 0, then we stop. Otherwise, we will have a new interval, which is half of this second interval. So this means a quarter of the initial interval, and so on. Then we have the following alternative. Either the algorithm stops after a certain number of steps, and this means we found a solution of the equation, or the algorithm does not terminate. In this case, Bolzano proves that the sequence of midpoints converges to some limit point x star, which is exactly a solution of the equation. Moreover, since we have this mechanism of halving intervals, we can easily obtain that the distance between xn and the limit point x star goes to 0 very fast, at least faster than this exponential b minus a divided to 2n plus 1. Now this opens also the way to do approximations, because suppose we want an approximation of x star within a margin, let's say error epsilon. Now it is sufficient to determine an n, so a number of iterations of the algorithm, such that this quantity is less or equal than epsilon. Now this happens if n is larger than log base 2 of b minus a over epsilon minus 1, which is remarkably a quantity that depends only on ab, the endpoints of the interval, on epsilon, the error, but not on f. Now let's see the application of this algorithm on the equation we introduced before. So we have the equation e2x plus x equals 0. Here we notice that the function f is clearly continuous on the interval minus 1, 0. The value at minus 1 is negative. The value at 0 is positive. And therefore, between minus 1 and 0, there is a solution. Moreover, if we want to determine that solution with an error of 1 over 100, what we have to do is a number of iterations which is larger than this quantity. Now the length of the interval is 1, epsilon is 1 over 100, so this log is the log of 100, which is about 6 point something, minus 1, 5.64. So this means that, since n is natural, for n equals 6, with 6 iterations, the corresponding xn will provide an approximation within this error, and we get this value, minus 0.56. What's next? Well, now it's your turn. I would suggest you to start by implementing the bisection algorithm, for example in a spreadsheet, and determine solutions for the following equation with a margin error less than 1 over 1000. If you want to dive deeper into abstract reasoning, there are plenty of interesting problems, like, for example, this one for you to try solving. This is just an abstract version of the problem we have seen here with the equation e2x plus x equals 0. Good luck and nice study.